as soon as the recording. There we go. Okay, welcome everybody to the second in our weekly California Dreams Microelectronics seminar. We're glad to have those of you who are returning back and those of you who are new. And we are excited today. We are going to have Professor Payam Heydari from University of California, Irvine, talking to us about his work in RF microelectronics. I'll let him give you his title from his slide here. Payam is an important part of the history of RF microelectronics that we talked about in last week's seminar. Payam got his PhD from the University of Southern California, which we are very proud about, and has since been at UC-Irvine, where he is the Henry Samueli Faculty Excellence Professor and University Chancellor's Professor of Electrical Engineering and Computer Science. That makes a connection with last week's seminar and the discussion that Peter had about RF microelectronics in Southern California, where Henry Samueli started his career at TRW after going to school and growing up in the Los Angeles area, moving on to UCLA, and from there he co-founded the Broadcom Corporation, and ultimately his greatest accomplishment was endowing a chair at UC-Irvine, which Payam now occupies. So with that, I will turn this over to Payam. Thank you, Payam, for joining.
Thank you very much. Welcome, everyone. It's a pleasure to speak at the California Dreams Technical Series. The subject of today's seminar is novel integrated circuits and systems covering radio frequency and millimeter wave. I also mute my video in case if there is a problem with the connection, so you can follow my presentation without any interruption. Before going deep into the presentation, I would like to give a brief overview of our research activities at Nanoscale Communication Integrated Circuit Labs, or NCIC labs. We have been conducting research in several major topics or thrust areas in the ultra-high speed millimeter wave terahertz transceiver project, which is one of the themes covered in today's seminar. Our specific objective has been to design innovative transceiver architectures that overcome inherent challenges associated with conventional architectures when dealing with very fast data rates. The data rate we are talking about is around and above 50 gigabit per second wireless connectivity. Within the thrust of millimeter wave and terahertz imaging and sensing, we have demonstrated integrated passive imaging receivers and active sensing transceivers with broad bandwidth enabling less than 0.5 Kelvin noise equivalent temperature difference, and in the case of the active imaging, millimeter scale range resolution. In another major thrust, we aim at designing high-performance building blocks and wideband radio frequency receivers. As part of today's seminar, I will share design techniques for a CMOS wideband blocker-tolerant receiver, which employs a novel local oscillator leakage suppression technique. Moreover, we delve into the exploration of custom millimeter wave terahertz building blocks. One notable example is to design a vertical impact ionization avalanche transit diode, we call it V-impact diode, with negative resistance at frequencies above the maximum operation frequency of the device. In our project, we showcased the first and highest frequency phase-locked synthesizer in silicon operating at 300 gigahertz. And together with my colleagues at UCI, we have designed artificial metasurface antenna based on dog bone structure and a wideband aperture coupled stack patch antenna on flexible material applicable for 6G. I have also been the PI for Center Scale National Science Foundation CPS Frontier project on brain-machine interface. I'm not going to go through the detail of this part of the project because this project is not within the scope of this presentation. So let's look at some of the design techniques for integrated sensing, integrated circuits and systems covering radio frequency and millimeter wave. Okay, so the two major use cases for radio frequency and millimeter wave integrated circuits are communication and sensing. When it comes to the communication, in order to understand the trade-offs and challenges maybe the best point to start is look at the Shannon's famous theory for MIMO capacity and the channel capacity. According to this formula, and I'm not going to go to the details, a number of very intuitive observation can be made. For example, the channel capacity C increases linearly with bandwidth, and it will logarithmically increases with the signal-to-noise ratio. Also, I have the intention of including this MIMO capacity to also mention that as a result of this multi-antenna communication, a number of benefits can also be attained. For example, a special multiplexing gain, where with more antennas in both transmitter and receiver side, now the system can support multiple data streams. Each pair of the transmit-receive antennas, in fact, can effectively create independent communication path that will lead to increase in total capacity. Another contributor to the boost in the channel capacity when we are looking at MIMO communication is diversity gain. Increasing the number of antennas, indeed, improves the reliability of the communication link through what we call diversity gain. This helps combat fading and reduces the probability of the deep fades, thereby enhancing the channel capacity. And finally, another benefit of using the MIMO systems is in the form of the beamforming gain. With more number of antennas, the system can now focus the transmitted signals more effectively toward the receiver, thereby achieving beamforming. This in itself leads to an increase in the received signal strength, improves signal-to-noise ratio, and as we know, the signal-to-noise ratio increase will affect or positively affect the channel capacity. Another very important formula that perhaps would be the centerpiece for our observation is the relationship that we have between the receive power and the other in a wireless communication link and the transmit power and other parameters. Based on this formula, we see that the received power out of a wireless channel improves with higher transmit power and is degraded quadratically with frequency, which mandates higher transmit power for a given distance. And as you can see, as we increase the frequency, carrier frequency, unless we use the higher transmit power, the receive power will reduce. Now, when it comes to sensing, in particular, looking at, for example, frequency modulated continuous wave or FMCW radar, which is based on the transmit and receive or radiation of what we call a single tone or chirp and reflection of the chirp and measuring the distance, we see that there are two major formula determining the performance of the sensing. One is the radar range, the maximum radar range, which according to this formula increases with larger signal wavelength. It is a function of the target cross-section. And as the bandwidth of the signal or chirp, in particular, when you're dealing with the continuous wave type of radar sensing, we see that the radar range is inversely proportional to the bandwidth. And with a smaller noise factor, obviously, on the receive side, the radar will increase, the radar range will increase. Another important notion is what we call range resolution, which is a key radar performance metric that defines the minimum distance between the two closely spaced targets that can be distinctly identified by the radar in a single chirp interval. In the so-called FMCW radar, this radar resolution, this radar range resolution is inversely proportional to the chirp bandwidth. So based on these two major use cases, it seems that an increase in bandwidth will lead to some performance improvement. In particular, in the communication channel, it will lead to higher channel capacity. And in the case of the sensing, it will lead to better range resolution. However, it seems that once we want to increase the wider bandwidth, we achieve the wider bandwidth, there are some challenges, both on the logistic part and on the technical side. On the logistic side, for frequency range of interest from 300 megahertz to 3 gigahertz, where many radio frequency channels and standards are located, we see that there are lots of standards or lots of applications congested in these frequency bands. So the increase in bandwidth is not really a possibility, particularly if we see that the channel per user or allocated per user is very limited. On the technical side, increasing bandwidth will bring along a number of challenges. In particular, the fractional bandwidth greater than 20% is challenging if traditional RF techniques are adopted. And I would like to emphasize the word traditional here, because in my presentation, as you will see, we are using a number of techniques in order to increase the bandwidth, and these techniques are so-called deviating from the traditional RF techniques. One traditional RF technique is obviously higher order filters to implement wideband matching circuits. Consider, for example, or compare an LC tank circuit, and let's compare it with a transformer coupling as a one interstage matching network. You will see that for narrowband circuit, the use of a parallel RSC tank circuit, for example, or parallel LC tank circuit will give us enough selectivity. But if you want to increase the bandwidth, we have to increase the order of the filter. One example is this double-tuned network realized using the transformer. And we see that then in terms of the occupied chip area and system area, the higher the number of passives, the more the area consumed by the system, and that is one important challenge. On the sensing side, generation of the robust linear chirp with a wide tuning range is very challenging. In other words, the chirp linearity is very difficult to maintain over a wide tuning range, and this is because one widely used tuning mechanism is the use of the varactors. And if you look at the structure of a MOSFET varactor, you see that the maximum capacitor achieved by the varactor over the minimum capacitor, first of all, follows a nonlinear profile. And second of all, you see that this so-called tuning range is very limited. So because of these challenges, having a wide bandwidth over and the RF frequency of interest anywhere from 300 megahertz to 3 gigahertz, which is widely used, is very difficult. One important, perhaps one observation is to increase the carrier frequency. Increasing the carrier frequency, let's say from 3 gigahertz to above 3 gigahertz, from 3 gigahertz to 30 gigahertz, which is the domain of the millimeter wave frequency range, and from 30 gigahertz to 300 gigahertz, which is higher side of the millimeter wave, you see that in this frequency range, as we increase the frequency range, a number of benefits will be attained. Increasing the carrier frequency will essentially allow us to have wider absolute bandwidth. Consider, for example, this cartoon where our goal is to achieve 6 gigahertz bandwidth. This 6 gigahertz bandwidth around a 10 gigahertz center frequency results in or mandates a 60% fractional bandwidth. Whereas if we increase this carrier frequency to about 200 gigahertz, then this fractional bandwidth will be around like 2%. 3%. So we will see that then the fractional bandwidth is getting smaller as a result of increasing the carrier frequency. And also the passive footprint, in particular inductors and even radiating elements inside the chip, will become smaller. Consider a dipole antenna, which we fabricated a number of years ago, 12 years ago, in 32 nanometer CMOS process, supposedly radiating 200 gigahertz signal. You see that, first of all, the none of the two spacing is only 820 micrometer. And you will see that the dipole antenna here itself is a small size to the extent that we can bring this antenna on chip. The notion of having a smaller footprint components allow us to also increase the complexity of the integrated circuit inside the chip. In particular, we can increase the number of antenna elements. If you want to have, if you think about a MIMO with large number of antenna elements, then increasing the frequency, leading to a decrease in the passive footprints, and that allows us to cram more elements inside the given real estate. However, there are a number of concerns that is associated with increasing the frequency. If we think about silicon integration, we see that the maximum operation frequency of the commercially available CMOS process is around 400 gigahertz. And that means that if we cannot really increase the frequency to any range we want. And also the intrinsic noise figure and the available gain out of a single device is also getting degraded. You see that the noise figure of the device will increase with frequency. Likewise, the maximum available gain will decrease. Another important factor coming from the nature of the communication is the path loss. As we increase the frequency, we see that the path loss will increase quadratically with respect to the frequency. This means that the air is really acting like a brick wall when it comes to communication of high frequency signals, for example, above 100 gigahertz. Not to mention also atmospheric attenuation, which increase quite dramatically at frequencies above 100 gigahertz. With all of these challenges being made, it seems that then we have to find other ways or mechanisms to overcome the limitation of frequency and bandwidth, yet improving the performance of the communication link and the sensing process. When it comes to the communication, a number of techniques can be employed in order to improve the performance of the communication link. For example, transmitting or receiving more bits through phase, amplitude, or polarization modulation. In particular, the deployment of complex symbol encoding with advanced modulation techniques, such as 4 to the M quadrature amplitude modulation, or QAM, which is part of the talk of this, which is part of the today's presentation. Also, we can use dual polarized antennas, dual polarization, and then improve the bit rate by basically using the polarization diversity. Another technique is to enhance the transceive efficiency. For example, over a given bandwidth, we perform full duplex communication, which means simultaneous transmit-receive over a single channel. Or increase the number of antenna elements, as you can see from the Shannon's theory for the MIMO capacity, increasing the number of antenna and thereby coming up with the antenna array, help us achieve the spatial multiplexing, diversity, and beamforming. All of them lead to an increase and improvement in channel capacity. Also, we can use still wideband communication with great IF selectivity, but using some non-traditional circuit techniques in order to improve the real estate of the chip, reduce the real estate, coming up with techniques, signal processing techniques that allow us to achieve wideband signaling without the use of higher order filters or matching circuits. On the sensing part, if you want to achieve a better range resolution, we have to increase the tuning range of the chirp-based radar circuit. But as we can see, as I mentioned, achieving wide tuning frequency synthesizers, wide tuning chirp generator circuits is very challenging. How about breaking a wide tuning chirp to smaller synchronized subchirps? This leads us to a whole new generation of segmented step chirp architectures, which I'm going to talk about a little bit in this presentation. Another idea to accommodate wide tuning and wideband signaling is to think about time domain processing rather than frequency domain processing. For example, going back to the era of pulse radar and use impulse or pulse-based radar in order to do the simultaneous processing of all the frequency components by performing the time domain signal processing for the radar and sensing. So that basically leads us to perhaps new generations of the pulse radars versus the FMCW radars. In this presentation, I'm not going to talk about the pulse radars, but I would like to refer you to our paper published 15, 16 years ago on the fully integrated radar on chip based on the pulse radar architecture. In this presentation, I'm going to talk about the segmented step chirp architecture as part of this presentation. Okay, so based on what I just mentioned in the introduction, I'm going to talk about the wideband blocker tolerant architectures at RF frequencies covering 400 megahertz to 3 gigahertz with minimum number of inductors, I will talk about the power-efficient end-to-end millimeter wave transceivers that employ high-order modulation while achieving extremely low power. And then finally, I will present techniques to achieve radio frequency and millimeter wave radars with wide tuning range, thereby potentially achieving millimeter scale range resolution. First, novel wideband blocker tolerant receivers with excellent radio frequency selectivity and extremely small LO leakage. I'm basically summarizing two of our works appeared in International Solid-State Circuit Conference and Journal of Solid-State Circuit Conference a number of years ago. We'll talk about a number of interesting signal processing techniques in the analog and RF domain that which we employed in order to achieve wideband receivers with great RF selectivity, yet extremely small local oscillator power. So the outline of this part of the presentation is as follows. First, I go to the introduction and motivation. Then we'll talk about the architecture evolution. Then we'll share with you the receiver design in 45 nanometer RFSY process. Then we'll share the measurement results, and finally a summary of this part of the presentation. Conventional multiband, multi-standard receiver systems usually incorporate multiple narrowband receivers to cover the whole frequency range of interest. This kind of system mandates bulky, costly, and fixed frequency filter banks, which incur excessively large number of hardware overhead. On the contrary, a single wideband receiver with tunable RF selectivity is highly desirable to replace these multiple receiver systems. It not only reduces the overall system cost and design complexity, but also leads to the new radio applications such as software-defined or cognitive radios. Such new applications significantly improve the spectral utilization efficiency in the already very congested radio bands at frequencies below 3 GHz. However, blocker tolerance and high quality factor tunability are the two major challenges for wideband receivers. The empath or mixer-first technique has been proposed to address these two challenges. The operation principle is based on the low-pass to bandpass impedance upconversion by driving the switches with non-overlap multiphase LO signals. When the switching branches are in shunt with the signal path, like this circuit, then they operate as an N-path-based bandpass filter followed by a wideband LNA. When the switches are in series with the signal path, the operation can be viewed as a direct down-conversion mixer-first topology. However, this technique suffers from a strong LO leakage due to the lack of the reverse isolation between the switches and the antenna, as you can see here in this slide. The dilemma of the conventional approach when you're using N-path type architecture is that the low pass to bandpass impedance upconversion has to be done by switches. If you want to have selectivity right after the antenna interface, to attenuate interference as early as possible, switch direct connection to the antenna using the so-called traditional technique is inevitable. Due to the low antenna impedance, typically 50 ohm obviously, the switch sizes must be very large, inducing large LO leakage. However, if we could conceive a frequency selective resistance with low out-of-band resistance at the input, we can basically filter the interference. And therefore, there will be no need for impedance upconversion, and we can avoid direct switch connection to the antenna altogether. This can potentially achieve a much lower LO leakage while preserving the high quality factor bandpass filtering capability at the receiver input. But the question is, how can we realize a frequency selective resistance? Here, we propose a bandpass common gate structure as a solution. We use an active notch filter in the feedback to implement a bandpass input resistance for a common gate stage. The notch filter is realized using the so-called empath technique in order to avoid the bulky inductors at frequency range of interest, in this case, below 3 GHz RF frequency. At the LO frequency, which is the frequency of interest, the notch exhibits a low gain, and the whole structure is not from a traditional common gate stage with proper input matching. At the so-called blocker frequency, however, the loop gain here, where the notch is part of it, is very high, which translates to a low impedance at the blocker frequency. For example, if the gain is 9 times, the input resistance is reduced by as much as 10 times, leading to a 5 ohm input resistance. This low input resistance at the blocker frequency suppresses the blocker voltage swing right at the input of the common gate stage. How to implement the notch filter? Without going through the details, you see that the notch filter is implemented using a type of empath filter. And in order to avoid the LO leakage to the antenna, we are using unilateral amplification through A1 and A2, the active stages. And by properly designing these amplifiers in the design, we avoid the LO leakage right at the antenna juncture. One problem with the bandpass common gate structure is that although the blocker voltage is suppressed at the input node, an enlarged blocker current, which I'm showing here, will flow through the common gate device and can attenuate the following circuitries if we are not taking care of this large blocker current. This enlarged blocker current must be steered away from the signal path. But how can we do it? In doing so, we add a blocker sink circuit in order to provide a low impedance path for this enlarged blocker current. It is based on, again, an active empath filter design, which allows for smaller capacitances and switches inside this block. The blocker current, in fact, passes through this active empath filter and is eventually absorbed by the amplifier output in the blocker sink. And therefore, the voltage swing at the input of the blocker sink, which is on the signal path, as I will show when I disclose the receiver architecture, will be kept very low. The signal at the drain of this common gate stage can be down converted by a voltage mode passive mixer followed by a baseband amplifier. However, such arrangement presents a bandpass input impedance for the signal path, and the blocker current can still enter the signal path depending on the impedance division between the blocker sink and the main signal path. In order to avoid this, what we want to do is that we really want looking into the signal path is a notch-shaped impedance, as I'm showing here. This signal path, as a result, presents a low impedance at the signal frequency, while blocker sink provides high impedance so that the majority of the signal current enters the signal path. At the blocker frequency, the signal path should present a high impedance, as I'm showing here, at the blocker frequency, so that the blocker current cannot enter the signal path. As a result of this bandpass impedance in parallel with the band stop impedance of the signal path, the blocker current and the signal currents are separated at the drain of the bandpass common gate stage. The band stop input path here is realized by using a frequency translational feedback in the down conversion path. In other words, we are implementing a shunt feedback where the mixer is part of this shunt feedback path in order to implement or realize a notch-shaped input impedance in the signal path. The signal frequency input impedance is lowered around 200 ohm due to the large shunt feedback resistance of 2.5 kilo ohm and due to the fact that the loop gain of this shunt feedback is very high. The 200 ohm input resistance at the desired frequency still provides around 12 dB of voltage gain for in-band signals to suppress the noise contribution from the latter stages of the receiver. The down conversion path also employs a large transconductance stage to further amplify the signal and to achieve a low noise operation. A blocker frequency located at large offset from the desired frequency indeed leads to this, causes this loop to exhibit sufficient loop gain such that the blocker is going to be suppressed by the translational feedback that is placed in the feedback path. Now let's look at the noise figure and the IM3 limitation in the proposed architecture. And let's see how we can address it. If you recall, we had a blocker sink in order to make sure that the blocker current doesn't have any way to the main signal path. We were using also a translational feedback in order to create a specific notch-shaped input filter or input impedance in order to make sure that the signal signal path and the blocker path are separated. Now, in order to do the in order to achieve a low noise figure, what we do is that we are using a noise cancelling technique comprising the main path and this auxiliary path that is emerging from the source of the bandpass common gate stage in order to do the noise cancellation. So the noise from the bandpass common gate structure can limit the minimum noise figure, especially the noise coming from the common gate device and this amplifier that is in the feedback path of the common gate stage. What we do again is that we are basically using this dual path noise cancelling mechanism in order to cancel the noise, thereby improving the noise figure. Interestingly, we also found out that this dual path signaling will take care of the IM3 rejection, thereby improving the linearity of the entire receiver. Shown here is the entire receiver architecture. As you can see, the receiver doesn't employ any inductor. We are using off-chip RF chokes for the biasing, but besides that, we are not using any kind of passive component in order to do the wideband matching. As you can see, this receiver is capable of operating from between the frequencies from 300 megahertz all the way to 2.5 gigahertz. So it's a wideband receiver with great RF selectivity. The prototype receiver manufactured in a 45 nanometer RF-SOI process occupies an area of around 1.05 square millimeter of active area. Chip on board packaging was used with 0.5 millimeter input wire length. Two types of PCBs were implemented for this measurement. The first PCB uses high self-resonant frequency inductors as RF chokes. This kind of RF choke exhibits less than 0.4 dB of loss, but the bandwidth associated with this RF choke is very limited, limited to around 3 gigahertz. However, this is sufficient when measuring the signals within the operation frequency up to 2.5 gigahertz. We also perform some harmonic measurement, and in order to achieve harmonic measurement, we use another PCB and we use another wideband RF choke to be able to perform the harmonic measurement for frequencies up to 8 gigahertz. Of course, this kind of RF choke for PCB2, which was used for harmonic measurement, has a higher loss. Now I'm going to show you some measurements that we got to prove that the LO leakage is excellent and we got great RF selectivity. The measured S11 or input return loss with respect to frequency is shown here. The measured S11 with varying LO frequency shows excellent high quality factor RF selectivity from frequencies starting from 200 megahertz all the way to 2 gigahertz. Also, a typical Smith chart at 1 gigahertz shows around 8 ohm out-of-band input impedance, which is equivalent to 12 dB out-of-band attenuation and RF input. That also shows a great blocker tolerance, at least on the receiver side and at the front end. The LO leakage in the receiver band was also measured across the operating frequency for three dies. For die 1, we see that we can achieve minus 92 dBm of LO leakage power at 0.2 gigahertz, minus 80 dBm, around minus 80 dBm at 2 gigahertz LO leakage power, which is shown in the screen capture of the spectrum analyzer. There is some variation between the three dies, as you can see here, due to the mismatch, but the trend is consistent. And you see that at least the LO leakage power is better than minus 80 dBm, much better than what we see from the prior work. The small signal noise figure measures a typical flicker noise corner of around 800 kilohertz, and you see a flattening of the noise figure after 2 megahertz. The whole receiver noise figure upon optimum noise cancellation can be less than 2.5 dB across the band. In fact, the minimum noise figure is around 2.1 dB for frequency range of interest from 200 megahertz to 2 gigahertz. The measured blocker noise figure was around 6.7 dB for 0 dBm blocker at 80 megahertz offset. Also, we performed linearity measurement for the LO frequency of 1 gigahertz, The out-of-band IIP3 for offset frequency of 100 megahertz is around 14 dBm, whereas the out-of-band IIP2 for the offset frequency of 100 megahertz was 60 dBm. In order to showcase and compare our receiver with prior work receiver, you see that as we can see in the table, the prior work, which is capable of providing high Q selectivity at RF input, generally suffers from a very bad LO leakage, high LO leakage in the receiver band, because many of these prior work are based on the N-path-based mixer-first topology. The more conventional LNA-first receiver architecture exhibits a much lower LO leakage, like the works that you see here and here, these two works, at the cost of the degraded blocker tolerance. In our work, we see that the noise figure is very good. The LO leakage is excellent compared to the mixer-first topology. And you see that the blocker tolerance and the out-of-band IIP3 and IIP2 is excellent as well. So this part of the presentation, in fact, gives us one important important teaching. By using some very sophisticated signal processing on the receiver side, we can achieve wideband operation. We can achieve also great IF and RF selectivity. And as a result, and while mitigating the use of the expensive, bulky passive components. In summary, for this part of the presentation, we propose a receiver architecture that realizes high quality factor RF input selectivity with a very low LO leakage level. The prototype receiver achieves 14 dBm of out-of-band IIP3 at 1 gigahertz with less than 2.5 dB of noise figure for frequencies from 0.2 to 2 gigahertz. The noise figure degradation, the noise figure at the 0 dBm blocker is 6.7 dB, around 4.4 dB noise figure degradation at the 80 megahertz offset frequency. The receiver band LO leakage is less than minus 80 dBm, can go as low as small as minus 92 dBm, which is excellent. And thanks to the particular circuit technique that we use on the receiver side in order to achieve simultaneous high quality factor RF selectivity, yet very small LO leakage. If you recall, this, at the beginning of the presentation, I said that in order to overcome the bandwidth and bandwidth limitation and high frequency operation, one way is to improve and increase the sophistication of signaling. In particular, use the high order modulation techniques. The use of the high order modulation techniques, of course, has been commonplace in traditional RF circuits, but when it comes to millimeter wave and extremely high data rate transceivers, the implementation of the modulation and symbol formation at very high speed faces huge amount of challenge. In this part of the presentation, I will introduce a number of power efficient, ultra high data rate end-to-end transceivers that overcome these limitations. And for this, I'm going to go through a number of publications that we had recently on the subject matter. This part of the presentation, I will talk about the fundamental limitations of the conventional transceiver architectures in achieving ultra-high data rate efficiently. I will discuss novel transceiver architectures and we'll go over 5 case studies, and then we'll summarize this part of the talk. One major distinction of this part of the talk compared to the wideband RF radio frequency receiver is that in the previous part of the talk, we see I covered frequency range below 3 gigahertz, what we call the traditional RF frequency. As you can see in this presentation, I will showcase a number of transmitter receivers that operate above 100 gigahertz frequency. The purpose of this, the way that I basically organize this presentation is to show you at least the depth and the breadth of the research that we are doing in my research labs that covers frequencies as low as 2 gigahertz, less than 2 gigahertz, all the way to above 100 gigahertz frequency. Okay, generation of the high-speed, high-order modulation schemes exert a stringent requirement on the mixed signal and digital blocks. Besides a speed consideration, the data converter resolution is increased with the modulation complexity. The table that I summarize in this slide demonstrates a state-of-the-art high-speed DACs and ADCs. Note that the power dissipation reported by all the prior works exclude I/O and clock buffers and digital calibration and clock generation circuits. Also, these prototypes do not include the on-chip memory. So with the exclusion of all of this, nevertheless, we see that the ENOP, the effective number of bits and the resolution and the power dissipation are considerably compromised at higher sampling speeds. Specifically, the data converter's power dissipation poses a major issue for a 6G transceiver. Moreover, a recent study predicts that the power dissipation of clock generators for data converters will be increasing quadratically with their speed and resolution, and thus becoming significant at the speed of interest. For example, the lower bound of power consumption of the VCO with a quality factor of 10 used within a phase lock loop, which is fed by 50 MHz crystal oscillator with a phase noise of minus 150 dBc per hertz at 1 MHz offset for a 6-bit 50 gigasample per second ADC is around 1.7 watt. Add this 1.7 watt to around 1 watt of core power dissipation of the ADC, for example, showcased in one of the ISSCC papers by Broadcom, you see that the overall power dissipation of the data converter can easily exceed 3 watts. Also, 2 plots in this slide summarize a comprehensive survey of published ADC works in 2 forms. In the middle plot, showing the relative noise floor achieved by the ADC works between the 1995 to 2018, we see that there is a lower limit of minus 160 dBc can be identified for all the ADC works reported by the prior work. The plot of the Walden figure of merit versus the Nyquist frequency of the same groups of ADCs indicates a lower limit for the power per conversion step, which gets worse with sampling rate. This means that the higher sampling rate ADCs are incapable of achieving an arbitrarily high SNDR and ENOP. This is a fundamental limitation, and that means that if you want to achieve very high speed data conversion, we have to compromise on the ENOP and the power dissipation. Now let's look at the fundamental limitations of the modern transceivers. Most of the modern transceivers universally employ one of 2 widely used homodyne or zero IF and heterodyne or low IF receiver architectures. Research works on ultra-high-speed transceivers have not addressed a fundamental question. What is that question? What are the power-efficient solutions for the mixed signal and the DSP blocks of an integrated receiver and transmitter chipset aiming for data rates above 50 gigabit per second? The prior work so far, targeting 20 plus gigabit per second, have only designed transceiver front ends, where the entire back end has been implemented by bulky arbitrary waveform generator, AWG, or real-time oscilloscopes. I hope you agree with me that a transceiver front end with external bulky AWG or real-time oscilloscope is not a practical solution, let alone being a power-efficient integrated solution. While the achieved data rates by prior works are impressive, there is no discussion whatsoever by them on how to implement high-speed signal generation, modulation, and demodulation. In fact, the mixed signal design challenges for these systems remain unresolved and are believed to provide fundamental limitations. Based on what we have discussed so far, we state that the design of integrated ultra-high-speed end-to-end transceivers operating at higher side of the millimeter wave frequency range, based on the conventional architecture, is nearly impossible, or even if it's possible, the solution is very power inefficient and energy inefficient. Aiming for a bits to RF and an RF to bits receiver, we investigate a paradigm-shifting architecture based on realization of modulation, demodulation directly in RF domain. If such possibility comes to fruition, it leads to enormous advantages. For example, the power-hungry ADC and DAC will be removed, almost removed. It will relax the complexity of the baseband unit, and it will achieve a spectral efficiency. Our first attempt to design direct modulation and modulation directly on RF domain starts with a simple OK transceiver. Of course, the OK modulation and modulation can easily be done in RF domain. One example is a fundamental frequency transceiver operating at 210 gigahertz, implementing OK modulation and demodulation directly in RF domain. This work was fabricated in 32 nanometer process, and it was the transceiver was designed in 2011 and was published in 2013. On the transmit side, you see a 4-element power combining OOK transmitter operating at 210 gigahertz frequency. And on the receive side, you see a single element direct detection based receiver, again operating at 210 gigahertz. Shown also in this slide is the dye macro photograph of the transmitter receiver. Without going through the details and looking at the table of performance comparison, you see that the EIRP achieved by this work is much better than the prior work, particularly at the saturated output power. The EIRP was measured to be around 15.2 dBm, which was much better than the prior work. Also, the EIRP2, the DC power efficiency was around 1.4%, boosted up to 6.9% at the saturated output power. So at the point of publication 13 years ago, that was the first fundamental frequency above 100 gigahertz CMOS transceiver in the world. We basically extended the idea of direct modulation demodulation to higher order modulation. Shown here in this example is the implementation of 8 PSK directly in RF domain, thereby realizing an RF 8 PSK transmitter. The idea is very simple. We basically use a QPSK modulator and a pi/4 shifted version of QPSK, and combination of these two QPSK, pi/4 QPSK, and the QPSK itself. And the toggling between these two QPSK is done depending on the status of the third bit. Remember that 8 PSK signal obviously is comprised of 3 bits. Each symbol is comprised of 3 bits. The third bit is used to basically switch between the QPSK modulator or pi/4 QPSK modulator. So the idea is very simple. As a result of this idea, we were able to design an RF to bits to RF transmitter in 65 nanometer CMOS process. The transmitter architecture, the transmitter die photo is shown here. The 170 gigahertz LO signal injected to the pair of mixer is generated from an external 19 gigahertz source using 2 triplers. And the switching between the QPSKs is done in the LO part, mainly because we want to make sure that the RF side is not exposed to any kind of switching at RF frequencies. The measured 8 PSK constellation is shown here. The wireless link for this measurement was comprised of the prototype RF 8 PSK transmitter and an off-the-shelf receiver chain with a transmit-receive distance of around 20 centimeters. The receive constellation error vector magnitude was around minus 14.8 dB at 15 gigabit per second frequency. The typical bit rate was 15 gigabit per second, and the EIRP was measured to be around 4 dBm. The overall power dissipation from bits all the way to the antenna was only 560 milliwatts. By the way, this transmitter used a 2-element antenna array on chip in order to boost the radiated power. The case study 3 involves 8 PSK demodulation directly in analog domain, which as a result obviates the need for high-speed ADCs. In doing so, what we did, and the underlying idea behind this, is that we used multiple phases of LO in order to perform the 8 PSK demodulation. The conceptual block diagram is shown here. We see that this RF 8 PSK receiver employs an RF demodulator that incorporates 4 correlation-based detectors driven by 8 phases of LO, partitioning the IQ space into 8 partitions. This RF 8 PSK, the RF 8 PSK, as a result, leads to a compact architecture where on the front end side, we received the antenna, and on the receive side, we were able to extract the 3 bits of the 8 PSK symbol. The receiver architecture is shown here. We see that the 100 to 115 to 135 gigahertz signal is fed to the LNA. At the output of the LNA, we have the 1 to 4 transformer-based splitter. On the right-hand side, we see the LO distribution network, and on the bottom side, we see the entire digital signal processing that leads to the detection and extraction of 3 bits out of the 8 PSK symbol. The dye macro photograph is shown here, where everything is included, including the RF front end and the signal processing that leads to the 3-bit extraction. Also, the measured eye diagram at 36 gigabit per second is shown here. You see clearly the 8 PSK demodulation and detection using the three-level eyes. You see also the opening both on the horizontal side and on the vertical side for the eye diagram. The received reconstructed 8 PSK constellation is shown here. The overall power dissipation of this receiver was only 280 milliwatts. The case study 4 extends the idea of direct modulation in RF domain to higher order QAM or quadrature amplitude modulation. The formation of the quadrature amplitude modulation, the way that we conceive, is very simple. Consider that we have M QPSK symbols, where the QPSK symbols are the Euclidean distance between them are increasing by as much as a factor of 2 between any neighboring QPSK signals. If we vectorially add these QPSK symbols, we can basically come up with higher order modulation. Shown here is one example of 16 QAM symbol formation from 2 QPSK, one with a symbol spacing of 2D, the other one with a symbol spacing of 4D. If we combine them together, we can simply achieve the 16 QAM. This way of the QAM construction, in fact, brings along a number of desirable attributes. Assuming that the QPSK subconstellations each exhibit the same error vector magnitude or EVM, the EVM of the QAM signal generated this way is the same as the QPSK EVM. Since low EVM can be attainable for QPSK modulation at high frequencies, the generation of the QAM this way leads to potentially lower EVM compared to a traditional way of performing and realizing this modulation in the digital domain. As I said, in general, we can generate the high order 4 to the n QAM scheme by employing n QPSKs with constant magnitude ratio of 2 between any side-by-side QPSKs. Once these n QPSK subconstellations are generating RF domain, this iterative process involves only scaling and vector summation. Both of them are easily implementable using the RF domain, in the RF domain. One example is shown here. On the left-hand side, you see the simplified block diagram of RF 16 QAM transmitter, where the 4 bits are entering pulse shaping circuits, and then the output of the pulse shaping circuits are subjected to a pair of QPSK Gilbert cell-based QPSK modulators. The output of the QPSK modulators are added together, and the resulting 16 QAM signal is injected to the PA. Also, I'm showing the diameter photograph of the bits to RF 16 QAM transmitter here. We also perform a number of measurements. The measured transmitter constellation is shown here. We see that the measurement is done using a receiver setup located at 30 centimeter distance from the transmitter chip. The measured 16 QAM EVM at 20 gigabit per second was around minus 15.8 dB, around 1.2 dB less than the QPSK EVM. This degradation, 1 dB degradation on EVM is expected because of the non-idealities and because of the losses, the passive losses inside the circuit. Nevertheless, you see that the EVM is very good. Another important attribute of this approach is that rather than the power amplification of higher order QAM, we can basically move the power amplifier and bring it prior to the power combiner. In doing so, now each power amplifier only processes and amplifies a constant amplitude QPSK symbol. The QPSK power amplification above 100 GHz is challenging, but it is less challenging compared to a PA that should otherwise handle a high order, high PAPR QAM modulation symbol. So this is another attribute of this particular direct modulation QAM transmitter that allows us to relax the performance requirement of the power amplifier on chip. We extended this idea recently, and we showcased an RF64 QAM transmitter at our conference, RFIC 2024. And recently, we have also a journal Solid State Circuit 2025, that extends the idea of the direct modulation to 64 QAM. I'm happy to inform you that this transmitter was able to achieve 120 gigabit per second wireless transmission, one of the highest data rates that ever achieved by a wireless transmitter. The transmitter is comprised of 3 QPSK paths. I'm not going to go through the details, but we can see that each QPSK path has its own LO path. The LO path is boosting up the frequency, 30 GHz external frequency to 120 GHz at the juncture of the mixers. The QPSK modulators will provide the input to the PAs. The PAs, as I mentioned, are placed prior to the power combiner. That allows us to basically design the PA that can operate close to the PSAT without worrying much about the signal backoff, simply because the QPSK is considered to be constant amplitude modulation. We also use the pulse shaping in order to make sure that bandwidth, the transmission bandwidth and the modulation and communication is done efficiently. Fabricated in 45 nanometer CMOS SOI process, the transmitter dipole is depicted in this slide. And the transmitter occupies an area of 4.5 to 2.8 square millimeter. To realize the backside radiation, also noticeable in the transmitter, we see the antenna on chip. We perform the backside radiation using an off-chip silicon lens in order to improve the radiation power. To realize the backside radiation, careful consideration was given to both the PCB design and the assembly process. At the outset, a hyperhemispherical high resistivity float zone silicon lens with a 12 millimeter of diameter was selected to enhance the backside radiation. Also, you can see that a 3 dielectric layer PCB was engineered to evaluate the chip's performance. The foundational dielectric layer employs a 1.6 millimeter thick FR4. The incorporation of the chip, approximately 300 micron thick, introduced challenges in wire bonding due to the foundry PCB fabrication requirement for less than 0.2 millimeter height difference between the bonding interfaces. To address this challenge, we use a number of layers and we basically put them on top of each other. In particular, we use a Rogers material, 0.1 millimeter thickness, featuring 0.5 ounce of coppers on the top and bottom sides in order to elevate the thickness and to level the bond wire interface between the chip and the PCB. The arrangement matching the chip's thickness and including a 4.8 by 3.1 square millimeter cavity ensures the chip can be positioned within the cavity, aligning with the electrical characteristics projected in the simulation. An intermediate FR4 also enhances the PCB's layout flexibility for DC and low frequency signal routing. We use non-conductive epoxy with a permittivity of around 3.2 in order to stick the silica wafer to the chip PCB and silicon lens. We perform a number of radiation measurements. Shown here is the E-plane and E-plane radiation, where the great agreement between the measurement and simulation is seen here. Shown in this slide is the measured eye diagram for 3 different modulation settings for QPSK, 16 QAM, and 64 QAM. Very impressive eye diagram measurement was achieved. We were able to achieve 120 gigabit per second data rate at an EVM of minus 22 dB, in this case, minus 18.6 dB for OpenEye. Of course, for 16 QAM and QPSK setting, the measured EVM was better, but overall, these measured eye diagrams prove experimentally that this transmitter is capable of providing 120 gigabit per second data rate, which, as I said, is reporting one of the highest data rates in the world. This is the first bits to antenna transmitter, all integrated in CMOS technology. Finally, I would like to also talk about the sensing part, what kind of techniques we use on the sensing part in order to overcome the bandwidth limitation, which I spoke about at the beginning of this presentation. How can we design radars that can achieve both rather long range and excellent range resolution? I'm summarizing the 2 works that we did in collaboration with Professor Abbasi, one of my colleagues at UCI. The work was published for presentation in European Solid-State Circuit Conference and currently is under review for the Journal of Solid-State Circuit publication. So what is at stake is that when it comes to the sensing, if we design the radars at lower frequencies, we have to deal with 2 important challenges. Large wavelength of the radiated signal, which leads to the large lateral resolution limit. In plain English, if we decrease the frequency, of course, the antenna the antenna size is bigger, and therefore the lateral resolution is getting degraded. Also, if you want to improve the range resolution, we have to increase the bandwidth. But earlier in this presentation, I mentioned that a fractional bandwidth of more than 20-30% at RF and millimeter wave frequency is extremely difficult to achieve, particularly if we look at the difficulty that we face in designing the wideband transceivers with fractional bandwidth exceeding 30%. On the other hand, if we want to design a radar at terahertz frequency, we are facing limited generated power. The phase noise is degraded because the essentially worst noise figure of the device, the receiver sensitivity is degraded, and also we have to essentially deal with the physics, which is the excessive propagation loss that we face at very high frequencies. So in short, it is challenging to realize a high resolution sensing technology that also covers long range. 3 techniques have been deployed in order to design the radars, particularly on the transmit side. We see that, for example, we can have a multiplier chain and followed by a PA in order to make sure that the central frequency synthesizer of the chirp or the chirp generator is operating at lower frequencies. Of course, this solution is simplified, is a simple architecture, but it leads to poor power efficiency, and also the phase noise is not very good. It's poor due to the fact that we are using a multiplier chain in order to boost the frequency. The second solution involves designing a wideband VCO. A wideband VCO leads to poor power efficiency, particularly if we don't use PLL, the closing phase noise performance is also not good. We see that the chirp linearity is also affected, and that leads to the huge variation of a slope for the chirp generation when we are designing an FMCW radar. That is not a very good. That's not a very good attribute. Finally, a phase lock based transmitter or phase lock based chirp generator can create consistent chirp slope. It obviously has a very small closing phase noise, and the power consumption is acceptable. The problem with the PLL, similar to the VCO, of course, is that the tuning range is limited. A phase lock scheme is preferred due to the fact that the closing phase noise is small, and also we can achieve very good chirp linearity with some circuit techniques. However, again, when we want to design a wide tuning FMCW radar, a single PLL is almost impossible to design, particularly at lower side of the millimeter wave frequency or at RF frequencies. So in order to achieve long range and excellent range resolution, here is what we did. We didn't really increase the frequencies above 50-60 gigahertz. We decided to keep the frequency lower, on the lower side of the millimeter wave frequency range. Also, we decided to break the bandwidth, the excessive bandwidth, to a smaller bandwidth so as to achieve wide tuning range. In particular, what we did is that we proposed dividing the entire bandwidth into multiple smaller subbands, simplifying the design of the critical building blocks, such as antennas and front-end circuits. Each antenna and front-end circuit handling each subband now is obviously handling a smaller bandwidth. The multiple baseband signals emerging from each subband will combine to construct the same length of the baseband as that of the single chirp architecture. In other words, we are using a stitching technique that basically concatenate the baseband signals associated with each subband in the digital domain so as to achieve the same the same sensing scenario as that wideband single chirp FMCW radar. So dividing bandwidth into the smaller subbands leads to the step chirp architecture. A stepped chirp radar sensor can achieve a maximum range resolution of maximum range resolution that is inversely proportional to the overall bandwidth achieved by these subbands. The overall range resolution associated with this overall bandwidth is only obtained if the slopes of the chirps corresponding with each subband are identical. This requirement is extremely challenging to meet. In other words, we want to make sure that the slope of each subchirp is linear and they are the same. And almost impossible to achieve if we are using free-running VCOs, as there is no feedback loop to force the constant frequency difference between the subchirps and also maintaining the same slope. To resolve the unwanted variations of free-running oscillators while significantly reducing the power consumption of the radar, we propose a new phase lock-based step chirp generation architecture as is shown here. A simplified structure is shown here, where we see a reference PLL and we see the presence of the so-called mixing PLL. In general, what we do is that the n subbands with frequency coverage of overall bandwidth divided by n and a spacing of delta f, which is shown here, are realized using one reference PLL and n-1 mixing PLLs. We can choose mixing PLL to be of type 1 PLL so as to reduce the power dissipation. The outputs of each pair of adjacent VCOs associated with adjacent PLLs are fed to a mixer inside the so-called mixing PLL. Under the locking condition, the output frequency of the ith mixer, which we call F mix, for example, is locked to the mixer's difference frequency component. In other words, the output frequency emerging from the mixer and filtered by the low-pass filter is equal to the difference frequency component between the frequencies of the VCO1 and VCO2. By placing the mixer inside a PLL, the mixing spares are substantially constrained or attenuated. Following phase locking acquisition, this structure ensures that the phase difference between any adjacent PLLs remains the same and is equal to a constant delta F, which also promises the synchronized sweep of their corresponding chirps with respect to the chirp generated by the reference PLL. The other advantage of the step chirp architecture is that the phase relationship between any two adjacent PLLs, VCOs, are deterministic, which facilitates the baseband signal stitching that I mentioned in my previous slide. Shown here is the transmitter architecture comprising a reference PLL and multiple mixing PLLs coupled to the reference PLL. And the receiver architecture is very simple. In fact, each subband has its own front-end chain, and the combination of the signals and signal concatenation and the stitching is done prior to in the digital domain prior to FFT, or the fast Fourier transform. The complete circuit block diagram of the CMOS radar transceiver, a step chirp transceiver, excluding the antenna and the interface, is shown in this slide here. The proposed radar transceiver was fabricated in 22 nanometer FD-SOI CMOS, where the overall area is 4.5 square millimeter, including the pad rings. Each subband employs a series-fed linear array of microstrip patch antennas, as shown here, for their ability to provide broadside radiation. The key advantage of the phase lock step chirp architecture lies in its ability to enhance resolution by integrating multiple subbands. To demonstrate this feature, a radar field trial was performed at a distance of 50 centimeters, where the RF signals from both subbands were extracted separately, and the time domain IF signals were then combined, where you can see the time domain waveform of the IF signal emerging from this radar. You can see that also we did the FFT of the combined signal that is shown here. This FFT signal, that the FFT spectrum reveals a significant enhancement of the range resolution, where closely spaced peaks can easily be identifiable or distinguishable. For this measurement, the range resolution of each subband was 28 millimeter. And for the combined signal, the resulting range resolution was enhanced to around 14 millimeter. The far field EIRP measurement was also repeated for various distances, as you can see here, where a close match between the received power with that estimated from the Friis equation is observed. The peak EIRP also and the EIRP pattern with respect to frequency for the two subbands that we designed and fabricated is shown here, where the red curve shows the EIRP with respect to frequency for lower band or lower subband, and the blue one shows the EIRP with respect to frequency for higher subband. The power variation across the two subbands is attributed to the frequency band mismatch between the antenna and the PA, as well as a 3 dB loss for deviated PA output power, load impedance due to the process variation and shift in the operation frequency. Finally, in this talk, I briefly discussed several techniques for radio frequency and millimeter wave integrated circuits. I mentioned that essentially, if we want to design a wideband architecture to achieve millimeter scale range resolution for sensing, high data rate for communication, we need to devise a number of circuit techniques where I discuss a blocker tolerant radio frequency wideband receiver with excellent LO leakage cancellation. In this part of the talk, I mentioned a number of signal processing techniques based on the N-path filtering in order to achieve extremely good linearity, blocker tolerance, and excellent LO leakage. I then switched the gear to higher frequencies and presented a number of end-to-end transmitter receivers based on the idea of the modulation, demodulation directly in analog RF domain. And finally, I talked about the notion of breaking the tuning range of an FMCW radar into subchirps, thereby achieving a wideband radar. At the end, I would like to also mention that as part of my collaboration with the California Dreams Hub, our vision is to design, implement, and fabricate new classes of wideband integrated sensing and communication end-to-end transceivers with the following characteristics. We would like to make sure that the bit rate is high, the AIRP per channel is good, the noise figure is small, and we want to achieve excessively large bandwidth. The techniques that we are employing is applicable to lower side of the millimeter wave frequency, particularly FR3 bands. On the sensing mode, the so-called integrated sensing and communication transceiver promises to achieve the range resolution of around 50 millimeter or less than 50 millimeter, long range and excellent the angular resolution. In the end, I would like to acknowledge the contribution and the great contribution by my current and former PhD students, as well as my colleague, Dr. Aghasi, and his students. I would like to acknowledge the contribution of the California Dreams Hub as part of the Microelectronic Commons program, the contribution and the support of the National Science Foundation, Samsung Advanced Institute of Technology, Qualcomm, and Keysight Technologies, particularly Dave Ha and Jane Nakao, for providing measurement equipment. Our chip fabrications have been done in collaboration with Global Foundries, ST Microelectronics, and Tower Semiconductor. Thank you.
Thank you very much, Payam. Very interesting. Are there any questions?
I have a general question about you didn't mention a temperature in this presentation. How are those design affected by temperature? It seems to me that the analog circuitry is highly influenced by the ambient temperature.
Okay, so for our university lab measurements, what we did, particularly for, let me go back to give you one example. So consider this example, this sophisticated transmitter. We basically performed the measurement for temperature around varying from around 10 degrees Celsius all the way to up to 30 degrees Celsius. So the performance was still very good. The reason for this is that for these transceiver architectures, we basically use lots of calibration mechanisms that I didn't go through. And those calibration mechanisms and lots of interesting techniques to do the PVT variation compensation. Therefore, for this circuit and also for our receiver circuit, the wideband receiver circuit, we saw a robust performance, at least for the temperature range that we did the measurement, which was anywhere between 10 degrees to 30 degrees Celsius.
Thank you very much. Your presentations are always very interesting. Thank you.
Thank you.
Thank you. We have another question from Tassin.
Yeah, thank you very much for this very interesting presentation. On this slide, you have the silicon lens to enhance the radiation from your antenna. I was just wondering if the main beam was perpendicular to this to the plane of your chip, or do you have an angle with the radiation pattern?
That's an excellent question. Yes. So yes, we use the silicon lens, and the broadside radiation was particularly peak of the broadside radiation, as you can see, was perpendicular to the antenna surface. And that is an excellent question, because what it means here is that, for example, if you want to use, if you want to extend this architecture to multi-antenna phase array architecture, perhaps the use of silicon lens is not good. The silicon lens is used here for this design in order to boost the radiated power, simply because we use an on-chip antenna. And the on-chip antenna that we designed had a very good antenna gain, but still is not good enough, right? So in order to increase the radiated power, we chose to use the silicon lens in order to kind of improve the radiated power. As you mentioned, then the use of the silicon lens will not give us an option to achieve beam steering mechanism or beamforming. And for that reason, if you want to use, if you want to use this architecture for beamforming, of course, we have to use another antenna arrangement. The antenna arrangement, by the way, is not part of the innovation. Of course, we use a very interesting antenna structure, but the antenna structure itself is not the central part of the innovation. The central part of the innovation is in this design is how to effectively do the modulation on the transmit side directly in RF domain, thereby lowering the power dissipation.
I see. Yeah, it's very interesting for you, this innovation part, but with a well-designed antenna, even with arrays, maybe you can make multiple antennas with not a single silicon lens, but a special way to extract the power from several antennas. In fact, that's also possible for, as I would say.
You're right, but look at the silicon lens that we use. I hope that I could show the board where we use the silicon lens. So deploying all these silicon lens, multiple silicon lens, is not really kind of desirable, particularly if you compare it with like a patch antenna or an antenna on package, which consumes less area. But yes, that's a good point.
Especially if you go to higher frequencies, if you work with high permittivity substrates, you will have all the substrate modes, and then you will need silicon lens to extract the power. So that's at above 100 gigs, you will have more and more the need of silicon lenses, in fact.
Absolutely. Yes, that's the reason we used it.
Thank you very much.
Okay. Thank you very much to Payam for the talk. Thank you to our audience for joining, and especially to those that asked questions. As we finish, I'm just going to put up our upcoming schedule. Next week, we are very excited to have Umesh Mishra from UC Santa Barbara. Umesh is the Dean of the School of Engineering at Santa Barbara, so we are lucky to have him in his capacity as a researcher as part of California Dreams, and also a founder of Transform, which commercializes some of the compound semiconductor work of the kind that's coming out of California Dreams, with his expertise in lab to fab demonstration. And also put up our points of contact for California Dreams, including the last one, which I didn't show last week, but which is our new YouTube channel, where this talk and all the other talks are posted. So thank you again, Payam, and thanks to the California Dreams team and our audience.
Thank you very much. Take care.
Thank you. Thanks, Payam. Bye.